Ends and beginnings. That's going to be a common theme in this module. And of course, this module is the end of the course, I'm afraid to say. It's module 12. And this module is going to deal with cosmology. Cosmology in chapter 19 is essentially the way that astronomy tackles some of the big questions that humans face, which is, where did everything come from? Where did it start? Where is it going? Those are pretty heavy questions. And a lot of you may be thinking, finally, these are really the questions that I wanted to study from day one. And you may wonder, well, why is this kind of at the very end of the course? As you'll notice, a lot of this stuff is pretty abstract. And it also requires a fair amount of knowledge of the concepts that we have studied during the course of the semester. It really doesn't, cosmology doesn't make sense unless you understand the physics that goes into star formation and star lifetimes, stellar lifetimes, and galaxy formation. All that kind of stuff is sort of required in order to make cosmology this very abstract concept, and some of the abstract concepts you're going to be facing this chapter. It doesn't really make sense unless you've kind of covered that earlier ground. So that's a part of the reason for putting this chapter at the very end of the course, despite the fact that it is really meaty and very interesting. At least a certain percentage of you are going to find it very interesting. Others are going to find this too abstract and rather mysterious. But I want to have you keep this in mind, that just because something seems mysterious does not mean that it's never going to be solved or answered. And that actually is well put by the author. At the very end of chapter 19, I'm going to read a little passage from something that the author wrote. As you review the history and structure of the universe, it is wise to recognize the mysteries that remain, but note that they are mysteries that may be solved rather than mysteries that are unknowable. Only a century ago, humanity didn't know there were other galaxies, or that the universe was expanding, or that stars generate energy by nuclear fusion. Human curiosity has solved many of the mysteries of cosmology and will solve more during your lifetime. Okay, so we're trying to answer the big question, how did it all begin? Well, let's consider the Big Bang. This is the idea that the observable universe, and I encourage you to review what observable universe means on page 428 of your textbook. The observable universe got its start as an infinitely dense, high energy state, and then expanded, cooled off, stars formed in galaxies, which are now moving apart from each other. That's the Big Bang theory, essentially in a nutshell. And I want you to also understand in this image that you see that you're not seeing a singularity within space. You're actually seeing the singularity from which space and time as we know them originated. So the Big Bang essentially created or started space. It's where they got their start. And from that, then all matter proceeded, forming stars, galaxies, etc. Now, want you to remember also, when we talk about the Big Bang theory, it's a scientific theory, just like we've talked about the solar nebula theory. That's the leading idea as to how the solar system came to be. And the theory in science, and I'll echo this again, is not just a guess, it's not just a hunch. It is an explanatory framework that accounts for observable facts and evidence. And so that's our goal for this chapter, is we're going to explore the various pieces of evidence that, taken together, support the Big Bang hypothesis, and thereby elevate it from just a compelling narrative told only for its entertainment value to a compelling theory based on observable facts. I'm sure I've talked in the past about the fascinating concept that astronomy allows you to travel back in time. And that's because light does have a finite speed. Light travels fast, but it does not travel infinitely fast. And so I wanted to actually kind of review this topic by talking about things that we can see in our night sky and how they allow us to do some time traveling. So let's go ahead and find one of the farthest objects we can see with the naked eye in sort of an urban setting, and that's actually the star Deneb, which is at the tail of Cygnus the Swan, and I'm looking at it today. It's actually a daytime star when I'm making this video here, but I'm going to go ahead and take off my atmosphere so we can see that star. So there it is. There's Deneb. It's part of a asterism called the Summer Triangle. And Deneb is a big old whopping star. It's got a magnitude of positive 1.25, so it is pretty easy to spot in the sky. It's not hard to spot. It's one of the brighter stars in the sky, and it is one of the farthest objects you can see with the naked eye in relatively light polluted skies, so sort of suburban environments. Its distance, you're going to get different numbers for it. Stellarium here is listing at about 3,000 light years away. You'll see numbers ranging from about 1,500 light years to 3,000 light years. That's really relatively unimportant. What is important to understand is that Deneb, the light that we receive today or tonight from Deneb, did not leave Deneb today or tonight. It actually left anywhere from 1,500 to 3,000 years ago. So we're not seeing Deneb as it is right now at this instant. We're seeing Deneb as it was 1,500 to 3,000 years ago. So if Deneb exploded today, we wouldn't know about it for another 1,500 to 3,000 years, depending on the exact distance. So that's one of the farthest naked eye stars. Now let's and think about that in context. 1,500 to 3,000 light years. That seems like a long way away, but think about the size of the Milky Way. The Milky Way we've talked is 75,000 to perhaps 100,000 light years away. So Deneb is actually, even though it seems like it's far away, it's actually a fairly close neighbor of ours. Now let's go a little bit farther out. Let's take a look at one of the farthest objects you can see with the naked eye. And this is going to be a cluster, a globular cluster entitled, it's called M13. It's a globular cluster in the constellation Hercules. And to the naked eye, it just kind of looks like a smudge. And we're going to zoom in on it to give you an idea as to what it looks like through a telescope. And what you wind up seeing, that smudge, when you put it in a telescope, winds up being, and notice the magnitude of this globular cluster is 5.9. So it's just barely naked eye visible. In dark skies, you can see it just kind of as a smudge. When you put a telescope on it, you see thousands of stars compressed into this small area. That's what a globular cluster is. Now remember, globular clusters don't typically reside in the disk of the Milky Way galaxy. They're more in the halo. And so we're actually not looking into the disk when we look in the direction of Hercules. We're actually looking a little bit off of the disk. So we're actually looking into the halo, but we are able to see this globular cluster, and it's about 25,000 light years away. So again, we're seeing this cluster not as it is today, but as it was 25,000 years ago. But again, that's still just scratching the surface as far as the size of the Milky Way. Again, these are all things that would be considered part of the Milky Way galaxy. Now let's take one more trip, and we're going to go to see the farthest thing away from Earth that you can see with the naked eye. And it's the only thing outside of our own galaxy that you can see with the naked eye, and that's going to be the Andromeda Galaxy, which is M31. So I'm going to type in M31 here, and here is the Andromeda Galaxy, roughly about 2.5 million light years away. So to the naked eye, it just looks like a smudge. When you put a telescope on it, you'll actually see not quite this beautiful. This is more of a long time exposure, but you will see essentially a galaxy shape, a disk. And again, this is not in our own galaxy. This is 2.5 million light years away. It's a galaxy unto itself. This is the collected light of 100 to perhaps 200 billion stars, all bound together gravitationally. So we're not seeing the Andromeda Galaxy as it is right now. We're seeing the Andromeda Galaxy as it was 2.5 million years ago. So again, this is why I stress astronomy allows you to time travel. And this is essentially what we talk about as look-back time. Okay, so now that we've sufficiently reviewed look-back time, let's move on to Olbert's question. It's listed as paradox in the textbook, but it's perhaps better just to be considered to be a question. And essentially, it starts by coming up with a little thought experiment. And the thought experiment is, imagine that you're lost in the forest. There's no marked trail, et cetera, et cetera. It's going to be dark. The question is, how can you get out of the forest in the most expedient manner? How can you get out there the quickest? Now, you look around in all directions, and the best way, of course, is to look for gaps between trees. And if in a certain direction you see a clearing in the gaps between trees, then you're going to head in that direction because that's going to be the edge of the forest. But if you look in a certain direction and there are more trees that are essentially filling up those gaps between the trees nearby, that means the forest continues further on in that direction. Now, if there's in every direction there are more trees beyond the gaps between the trees that are in your closest vicinity, then essentially you're doomed, as the forest would be just infinitely large, or at least large enough that the edges can't be seen. There's no way out. Well, Olbers posited the same question about the universe. He was asking, is there an edge to the universe, or does it continue on forever? And at the time, when he was thinking about this, the universe was assumed to be infinite in size, infinite in age, and static, meaning not changing. And so therefore, one answer would be, or the actual question or paradox is, if you do have a infinite in time and infinite in space or size universe, but static and filled with stars, then you would expect that in any direction you would be looking, you would eventually be looking in the direction of a star. Now, some may be closer, some may be farther, but we would be receiving light from all those stars. So the question is, why is the sky dark at night? If the universe is infinite, then every line of sight should eventually end on the surface of a star at some point, which means that we would be receiving light from those distant stars in absolutely every direction, and therefore we should have a nighttime sky that would be as bright as daytime sky. So that's the problem. That's the question, and we're going to move on to the answer on the next slide. Okay, to answer Olbert's question, we first of all have to remember that the farther we look out in space, the farther back in time we are looking. Remember, that's that whole look back time idea. So here's a three-dimensional representation of the galaxies observed by the Hubble Space Telescope in that Hubble Deep Field image that I mentioned back in Module 11. So as we look further out in space, it turns out we run out of galaxies to see, which actually does not mean that we've reached an edge in space. We're going back in time. And so we've run out of time, or more precisely, we've reached a time before galaxies existed. So the edge we see is an edge in time, not in space. And the actual answer to Olbert's question then is that the universe is not infinitely old, but actually has a finite age. So our next question is going to be, if the universe has not been around forever, how long has it been around? Okay, so here we actually see some of the data from which Edwin Hubble derived his Hubble's law. And you see on the graph in the lower right that we see the velocity of galaxies with respect to their distance away from the Milky Way. And apart from, there's a couple that are really close that are actually blue shifted a little bit. The velocity essentially is positive if the galaxy is moving away, but we see one that's actually moving close to us, which is actually true. The Andromeda galaxy is actually moving toward the Milky Way and is going to collide in about 5 billion years, and that's due to a gravitational interaction of that close galaxy. But other than that, farther away than that most close galaxy, all the other galaxies are moving away from the Milky Way. And what's even more interesting is the fact that the farther away they are, the faster they're moving away. And we see that in the redshift of the spectra of the galaxy. As you notice, as the distances, notice these are in megaparsecs, but these are distances. As we get farther and farther away, notice that the amount of redshift is increasing. And again, that shows up as the trend line there in Hubble's data. Okay, so this simulation shows us the light curve from a galaxy, and we see the intensity of the light versus wavelength, and we're seeing a galaxy that is pretty visible, or pretty easy to spot in the visible. And of course, this is a galaxy that is got to be pretty close because it doesn't have much of a redshift. But as Hubble discovered, the farther away your galaxy, the greater the redshift. And that's what I'm going to do. I'm going to just increase the redshift. And so a galaxy has the same spectrum, but is farther away, will be moving away faster. And notice that galaxies that are, in this case, pretty far away, and have a redshift of 1, would have a big, essentially, would have a big change in the spectrum And this is why, notice that there's not a whole lot of visible light being produced here. You're seeing much more of the light in the infrared and perhaps down even into radio wavelengths, which is why infrared telescopes, radio telescopes become very, very important in doing research about very distant galaxies, because the galaxy, even though it may be producing a spectrum that peaks in the visible, but it's moving away so quickly that that spectrum becomes redshifted into the infrared or the radio wavelengths. Okay, so the interpretation for the Hubble law is not that all galaxies in the universe are running away from the Milky Way, but rather that the universe is expanding and in sort of a strange sort of manner. And so we have what we call the raisin bread analogy, which is pretty useful because notice that the size of the galaxies, in this case the galaxies are the raisins, the size of the individual galaxies remains constant, and that's essentially due to the gravitational forces within the galaxy, but that the space between the galaxies, or the space between the raisins, is increasing. Now, why the space between galaxies increases is not readily explainable, but the expansion of space between galaxies is consistent with the observations behind Hubble's law. So it's not that the raisins are moving through space away from our galaxy. The raisins are essentially being carried along by the expansion of the bread, and the same thing is happening in the universe. It's not that the galaxies are moving through space, but rather they are being carried along by the expansion of space itself. Okay, please do keep in mind the limitations to these different analogies. Remember the raisin bread analogy, the limitation is that there is no crust to the known universe. So don't take it too literally. The raisins within the bread, that's useful, but don't take it too literally. Another variation on the theme is some coins on a balloon. So we've got this little simulation. We're going to let the balloon inflate. And notice that the coins themselves represent galaxies, and they maintain their scale. They don't get any bigger. Right? They maintain their size, and that's because of gravitational effects within the galaxy, but the space between them does indeed grow. Not because they're moving along the surface of the balloon, but rather the surface of the balloon itself is expanding. So again, that same analogy that the galaxies are not fleeing the Milky Way galaxy. Distant galaxies are not fleeing the Milky Way galaxy in that they are not moving through space, but rather they're just kind of being carried along for the ride as space itself expands. Okay, this expansion of the universe, of the known universe, is really crucial in being evidence for the Big Bang. Sometimes the idea or the analogy is of a movie projector. Right now we're running the movie forward. You could run the movie backward. So if the space between galaxies is expanding today, let's think about going backwards in time and considering how long ago was the space between galaxies zero. Well, it turns out that's what's called the Hubble age of the universe. We find that at the current rate, the space between galaxies is expanding. There was essentially no space between the galaxies at approximately 14 billion years ago. That's roughly 13.7. And that essentially gives us an estimate for the finite age of the universe. Okay, so this may look like a rather confusing graph. It's actually a graph from page 435 of your textbook. And it's got a lot involved here. There's some jargon you're not quite familiar with yet, but you will become familiar with it as we move through the chapter. But first of all, let's just talk about the general structure of this graph. We have temperature on the y-axis. On the x-axis, we have time. And notice the time goes from now back to essentially the Big Bang. So we go back in time from right to left. So right now we're 13.7 billion years after the Big Bang. And what we're going to do over the next several slides is we're going to go through the early stages of the Big Bang, or the early stages of the known universe, shortly after the Big Bang, essentially in reverse chronological order. We're going to move each step to the next older, hotter, and denser phase. Now, of course, our current understanding of physics doesn't extend all the way back to time zero. So we're only going to cover 4 major events in the early stages of the known universe. Okay, so as you'll notice, if you play the video snippet that I've got embedded into this slide, as we run the clock backward from the present day. Remember, we've already seen the first galaxies forming, and those were very low metal galaxies. Now we're going back to a place where there were no galaxies, where essentially the first generation of stars are born out of primeval hydrogen. And this slide, or this image up here, shows nebula that were created from these very early hypermassive stars. These hypermassive stars that formed from raw hydrogen excited the hydrogen atoms around them, creating gigantic emission nebulae. And the process of exciting these hydrogen electrons is called deionization, or I'm sorry, reionization, and that's discussed in your textbook on page 434. Okay, so remember where we were just at. We were just talking about the first stars being formed, the first galaxies being formed, and remember the way we're going. We're actually going this way. Right? We're going back in time, back to a older and hotter universe. So what's next then? Well, just before the formation of the first stars, we had essentially just hydrogen, this area right in here. Just hydrogen, no stars. That's what's called the dark age of the universe. That's described in your book on page 434. Now let's look a little bit further back, and we're going to essentially run into a figurative wall of light. We're going to look back and see photons from every direction. And that's what's called the cosmic microwave background, the CMB. And even though this is not the first radiation, the first photons ever created, these are the first and oldest photons that we are allowed to see. And they are detectable by using special radio telescopes, even old televisions with the old rabbit ears. The static you see is produced by the cosmic microwave background. So static snow on a television actually connects you to the Big Bang 13.7 billion years ago. So the question is, what would suddenly release, this wall of photons? Where do they come from? And why are older photons that may have existed, why are they not observable to us today? Well, we have to, again, remember we're going back, further back along this little line here. So way back in the early stages of the universe, shortly after the Big Bang, it was very, very hot and dense. The universe was so hot and dense that positively charged protons, negatively charged electrons, they were separated from each other. And they were moving around so much that they couldn't join up to make neutral atoms. It's kind of like a mosh pit. Think about a mosh pit of protons and electrons constantly just bashing into each other. And any photon, any particle of light in this hot, dense universe would continuously be kicked around and scattered. So light from that time and earlier could not have survived intact today. But as we get into this part of our little chart, we're starting to see these little steps here, where the universe is gradually cooling and expanding. Protons and electrons calm down enough that they can join up with each other. So that's what we've got, what's called recombination. But it's really just combination, as your book describes. The electrons and protons are now getting together. And so this is like, back to our mosh pit analogy, the protons and electrons calming down. Instead of smashing into each other, they pair off and they slow dance with each other. And the space on the dance floor then drastically opens up. And so now photons at this point are now free to travel without being kicked around and scattered. And so the cosmic microwave background, these now can be visible. These don't get scattered. And so these are the first oldest photons that started out from recombination. Okay, so it is important to understand that when we're talking about cosmic background radiation, today it is observable in using radio telescopes, really long wavelength, as if it was coming from a very, very cool source, around 2.7 degrees Kelvin, as is mentioned in the book. But at the time of the cosmic background, the cosmic microwave background radiation formation, when it actually formed, the temperature of the universe, this is right around recombination, was about 3,000 Kelvin. So now this stuff appears to be coming from a source that's about 2.7 Kelvin. So it appears to be much cooler than its moment of formation. Well, how is that possible? It's because of the rapid expansion of the universe. It was created as relatively short wavelength radiation, but because of the expansion of the universe, the radiation has been redshifted, and therefore it appears to be coming from a much cooler source. But that's only because of the rapid expansion of the universe, and that's why we attribute such a large Z value, a large shift value, to the cosmic microwave background. Okay, going back in time, even before recombination to an even hotter and denser time, the entire universe essentially resembles the core of a star, where temperatures and pressures are high enough for protons to collide with each other and fuse. And this is what's called the nucleosynthesis phase of the early Big Bang. Now, for a brief time in this early universe, hydrogen fused into helium in the cores of main sequence stars. But it can also fuse into deuterium, which is an unstable form of hydrogen, as well as lithium. What makes this early fusion in the universe unique is that deuterium and lithium cannot survive the high temperatures in the core of main sequence stars. Only helium survives. But the expansion and cooling of the universe shut off fusion such that deuterium and lithium from nucleosynthesis did survive to the present day. So all the deuterium, which is found as heavy water in certain springs on Earth, and all the lithium, which is used in batteries for hybrid cars, computers, and smartphones, all that lithium that's found today can only have come from this early universe fusion. Okay, so we've reached the last stage. We've gone the farthest back now. We're talking about, in this slide, the first matter, the stuff that makes up you, me, the rest of the universe. This is as far back as we're going to go, where the universe was essentially really hot, really dense. These are the conditions we produce today on Earth using particle colliders. In fact, I've got a video from the CERN particle collider down in the lower right of the screen. In particle colliders, mass and energy are readily interchangeable. If you give it enough energy, you can produce matter, and it turns out antimatter as well. So for this process of what's called pair production, if energy creates an electron, it must also create the electron's evil twin, which is called a positron or an anti-electron. Annihilation is the process where if an electron and a positron meet up with each other, they will be destroyed and converted back into energy. Everything that makes up matter has an antimatter evil twin. And the very early universe continuously converted energy into equal amounts of matter and antimatter, and vice versa. Okay, so now that we have some insight as to where the universe came from, we know a little bit about the Big Bang. The question is, what's going to happen to the universe? And that really depends upon the shape or the geometry of the universe. And there's still some debate about the shape of the universe, and so if you read the textbook, you'll see described essentially three different models for the universe. There's the closed universe, or a universe that has positive curvature. You have the flat universe, which is one that has zero curvature. Then you have an open universe, which has negative curvature, and all these things have implications for whether the universe will continue to expand, whether it will contract, etc., etc. Okay, this is the same diagram that you see on page 440 of your textbook, and this just essentially shows the expected fate of the different types of universe geometries. So for an open universe, you would expect that it would expand forever, and for a closed universe, you would expect it to essentially contract again. And a flat universe, you would expect to gradually continue to expand, not quite as rapidly as an open universe. Now, one thing that's very interesting about this graph is, and as you'll read in the book, the flat universe is now essentially the one that's agreed upon. But notice that there is a slight problem, at least the way this graph is drawn, that this would predict an age of the universe of being 9.5 billion years. And as we've already discussed, the universe is thought to be 13.7 billion years. In fact, if it was 9.5 billion years, that would really be a problem, because there are objects that are known to be older than 9.5 billion years. So it'd be weird to have things that are in the universe that are older than the age of the universe itself. This paradox, apparent paradox, will be sorted out before the end of the chapter. So of the different universe geometries, the flat one appears to be the most correct, but there are a couple of problems with the flat universe. There's first of all, the flatness problem. It seems to be nearly flat, and how did that happen? And also, the other difficulty is what's called the isotropy of the cosmic background. That means that in any direction you look, the cosmic background radiation appears to be essentially the same temperature. How did that happen? If the universe expanded so rapidly, the different parts of that universe couldn't have communicated with each other or come to an equilibrium temperature that they appear to have done. And so that's a slight problem with the classical model of the flat universe. Okay, so what's the solution to the problem? Well, it turns out that by observing enough type 1a supernovae, those are exploding stars, remember those are essentially white dwarfs that accumulate material from a nearby companion, and that material accumulates so much that it causes an explosion on the surface of the white dwarf, essentially blows the white dwarf to pieces. There's a certain expectation, or there's a certain characteristic of those supernova in how quickly they decline in magnitude. You know, they appear as a new star, kind of a flash of light, and then they slowly fade away. And astronomers studying these type 1a supernovae saw that the brightness of them was actually a little fainter than expected, and that meant that these supernovae had to be farther away than they were expected, and that indicated that early on in the formation of the universe expanded even more rapidly than originally expected. And that would indeed make the universe a little bit larger than the normal flat universe, or not larger, but older than the flat universe theory would indicate. So that would indeed allow for a universe that is 13.7 billion years old, as opposed to a 9.5 billion year old universe.
Quickly, here is the 1-minute history of people who have studied the origin of life. Aristotle thought that life came from decaying matter, like crocodiles came from rotting logs. The theories continued with people like Charles Darwin, who proposed that life could have started in a warm little pool. But it wasn't until the late 1920s that scientific experiments actually began to break down how life, or even the building blocks of life, may have chemically formed from inorganic matter. In the early 1950s, the Miller-Urey experiment showed that some of the building blocks of life could be produced from what was then thought to be an early Earth-like atmosphere and a lightning strike. The Miller-Urey experiment was later featured in Carl Sagan's series, The Cosmos, and the origin of life field had its first major foothold. In the late 50s, NASA was established and got busy catching up to the Russians. By the early 60s, NASA began formal experiments dealing with life in outer space. This experimentation continued through the next few decades and eventually resulted in the formation of the NASA Astrobiology Institute in the 1990s and the modern scientific study of the origin of life.
Okay, so as you just saw in the last video, we are moving from formal astronomy into what's called astrobiology, a very exciting field that combines both the some of the aspects of astronomy with the aspects of biology. Essentially, it's asking the question, how does life begin and how does it change as well? So first of all, perhaps in considering this, we need to start talking about, what does it mean for something to be living? What does a living thing do? Well, first of all, it should manipulate its environment, meaning that it needs to eat or build or destroy or whatever in order to grow and make a new generation of things that can manipulate its environment. So it's a living thing should be able to survive as well as reproduce. Now, in order to do things that living things do, and more importantly, to make sure that a future generation is able to continue to do these things, it requires a lot of information to be stored. And on Earth, this information is typically encoded in long, complex sequences of carbon molecules, although it is speculated that some other types of chemicals might also be able to encode this information. And that's what you're going to cover early on in this chapter, is some of the basic organic chemistry involved in astrobiology. Now, one last thing we need to add to our working definition of life is that in order to survive changes in the environment, a living thing should be able to adapt, either in its own lifetime or through changes in successive generations. Because conditions on Earth change over time, then living things on Earth have also changed over time. And that's what we call evolution. Another thing that we'll try to do in this chapter is to create a timeline for how life arose on Earth. Now, there are two things to consider here. First is that initially these steps take a long time to happen, but each successive step takes a shorter and shorter time to occur, so the rate of change speeds up over time. The second thing to consider is that this sequence of events is a hypothesis, and we will present evidence for each step. Remember, that's the whole nature of a theory or a hypothesis in science, is that it's an overarching explanation that does have evidence. There are facts and observations that the overall hypothesis is explaining. So we will present evidence for each step, whether through recreation of similar conditions or fossilized remnants. But to be completely honest, there will be one step in particular that has yet to be recreated or remnants to be found for, and we will be sure to point this out. Now, atoms have a tendency to hook up with other atoms to make simple and complicated molecules, as long as there's enough energy and enough time. It is not difficult to have building blocks, simple molecules, assemble naturally in a short amount of time. This isn't life yet, but it's a start, and it can be readily demonstrated by recreating conditions expected on the early Earth, and that's what was done in the famous Miller-Urey experiment from the early 50s. Okay, so chemical evolution is not life yet either, but it is the process by which simple molecules will assemble to form more and more complicated molecules. As you can see right here, that's a pretty complicated molecule. And given enough energy, the proper conditions, and enough time. And this is observed to happen naturally, and it's what you do in a laboratory if you ever need to take organic chemistry. Now, eventually, longer and longer molecular chains will build up, and at some point will begin to manipulate the environment and make new generations of itself. It will become self-replicating. This is the step that there is no fossil remnant for, and has yet to be observed in nature or deliberately created in the laboratory. But it is being actively pursued. Again, it's one of these things in science. Just because science has not does not know how it's done yet does not mean that it's going to always be a mystery. It's just a mystery that has not yet been solved. It should be pointed out that even though Miller and Urey and other scientists have recreated some of the very basic building blocks of life that could have happened just by virtue of natural processes in the early Earth, there's also a theory out there that none of that stuff would have been necessary. It could be done, but it didn't have to be done, because there's also the possibility that there could have been extraterrestrial origins for life, meaning that amino acids and simple organic compounds and molecules show up in meteorites all the time. And so it could be that life was seeded here on Earth just by virtue of the fact that a meteorite smashed into the Earth and provided those early building blocks without any need for the building blocks to be built here on Earth. Again, it's another theory. Right now, it's currently untestable. Now, here's a pretty cool website that it's called hereistoday.com. I encourage you, I'm making this video in January of 2016, but you're welcome to log on and play around with it for yourself. So again, essentially it just kind of puts time in context, or puts human life into context with respect to not only the age of the Earth, but also the age of the universe. So here's this month, etc., etc. Here is this year. And here we are in the 21st century. And then the millennia. We're in the third millennium. And then we get into a little bit of geology in that we are part of what's called the Holocene epoch that started about 11,500 years ago. And now we start to see the Quaternary period. Again, this is gone through in your book a little bit. Nothing to memorize here, but just to more important is to just kind of get the big picture. The fact that our lifespans, and even the lifespan of modern humans, as a scratch in the surface of the overall history of the Earth. Here we go all the way back to the Cenozoic. And again, these are geologic time scales. We're not really talking about life yet. And then here's the Earth. So the Earth formed about 4.6 billion years ago. Now we're going to start talking about biology. So right now we've been up to geology, and see how they have the different eons listed here. Now let's go ahead and move on into life. So about 3.6 billion years ago. So Earth formed about 4.6 billion years ago. For a billion years, nothing was really happening. Then all of a sudden, well, not all of a sudden, but about 3.6 billion years in the past, some very simple life forms began to appear. We had an oxygen atmosphere starting to develop about 2.5 billion years ago. And then finally, after essentially 4 billion years of not having any complex organisms developing, about 500 million years ago, the fish started to fill the waters. And then we started to get insects, vegetation, reptiles, small mammals about 200 million years ago, birds, and then Homo sapien, our species, modern man, has been anatomically about the same for the last 200,000 years. Now, to put it all in perspective, just the existence of the Earth compared to the existence of the universe. Notice that the Earth is only 4.6 billion years old, whereas the universe, which we've been talking about, is about 13.7 billion years old. So that kind of puts it all in perspective. I encourage you to check out this website. Again, the last slide I sort of went through a timeline, but I also wanted to talk about this timeline that's presented. This is the same graph essentially you see on figure 20.7 on page 463. And of course, it starts out with very simple life. Simplest life is essentially long molecular chains that contain enough information to manipulate the environment, and make new generations. You know, they're just good enough to survive and reproduce. Of course, it's got to have a protective cell wall, and it's got to be able to grow large enough to divide itself into multiple copies. Now, a single cell organism doesn't leave much when it dies. It's very difficult to fossilize, but you can have colonies of single cell organisms that do leave behind evidence, and that, of course, is the stromatolites that are discussed on page, let's see, 459 of your text. Fossil remnants of these colonies are indeed found today and can be dated to about 3.4 billion years or so. So when we compare that to the approximate age of the Earth, we see that it took a long time, essentially about 1 billion years, for the simplest form of life to arise from atoms and molecules. And as I mentioned, the pace of change increases then, because life gets more and more complex from here. Single cell organisms progress to larger organisms made of many, many cells working collectively underwater. Again, things are still essentially in the water. We're still talking about ocean life only. Living things start looking less like stuff that'll make you sick if you ingest it, to more tasty and nutritious forms about 500 million years ago. Okay, so 500, 600 million years ago, relatively recently. So if you ever build a time machine and forget to pack a lunch, don't go much further back than that, or you're going to probably starve to death. And of course, then as we see a more rapid rate of change. Each consecutive step for life to become more and more complex happens faster and faster. Not long after complex life starts in Earth's oceans, complex life arose on land. And of course, that's determined by, we have plenty of fossil evidence for that. And then not much longer after that, life on land becomes more complex, not only to become more populous, but to radically change its environment in doing so. So of course, that includes humans. We've not only changed quite rapidly, becoming more complex, but also have altered the Earth system quite a bit. So it did take a while for life to arise from atoms and molecules, and then become us. As is mentioned, humans, that's bipedal apes, have been around for about 3 million years. But Homo sapiens, our particular species, has only been around for the last 200,000 years or so. We've essentially anatomically unchanged in the more recent history. Okay, so we've covered the topics of, first of all, how life may have originated here on Earth, and then how it evolved over time. And now another area that astrobiologists are very interested in is life possible in other places other than Earth? So let's first of all, we are sort of biased. We have to consider life as we know it here on Earth. And it seems like in order for life to arise here on Earth, we need a few things. We need liquid water, we need an atmosphere, we need moderate temperatures. They can't be too hot or too cold because we need that liquid water. And liquid water only exists as a liquid under certain temperature and pressure conditions. So if water is necessary, then it seems like a certain temperature range is required. And you also need time. As we noticed, it took a long time for life, even the simplest of life, to evolve here on Earth. And then once we had simple forms, it took a long time to have more complex forms. So certainly you need time in order for life to arise on other places in the cosmos. Now, humans have looked for life, at least in other parts of the solar system, the moon, Mars, etc. And there is still hope for finding some pretty basic forms of life. But as far as intelligent life, that does not seem likely in our own solar system. And then beyond that, it's tough to go to those places. If you think about going to another star, our next nearest star is, of course, Proxima Centauri, 4 light years away. And that's traveling at the speed of light. It would take 4 years. So the travel times are just not possible. So the alternative then is to use radio waves, which travel at the speed of light. And so essentially we can either broadcast or we can listen or we can do both. Those are the ideas behind things like SETI, the search for extraterrestrial intelligence, where we're doing more listening than we are sending. And then there's also BETI, broadcast to extraterrestrial intelligence. So one of these places that we do broadcast from and listen from is what's called the Arecibo Observatory. It's in Puerto Rico, and in fact, it was featured in the movie Contact years ago with Jodie Foster. And back in 1974, from Arecibo, they broadcast a test message from that observatory. It was essentially a bunch of pulses and pixels that build up a simple but information-packed message to whatever advanced technological civilizations that might be out there. Okay, so what are the chances of there being a communicative other civilization out there? Well, Frank Drake actually decided to come up with an estimate. He developed what's called the Drake equation. We're going to kind of break it down. Now, the first factor in the Drake equation is this n with the asterisk. And that indicates the number of stars in the Milky Way. Now, recall, we can only see stars in our immediate vicinity, but we can estimate the overall size of the Milky Way and derive a relatively certain value for the number of Milky Way stars. And this is by far the most certain of all the factors. Of all these factors here in the Drake equation, this one is the most certain, and we've got pessimistic and optimistic values here, but essentially around 200 billion is a ballpark figure for the number of stars in the Milky Way galaxy. Now, the next factor is the fraction of stars in the Milky Way that have planets, more specifically terrestrial planets or rocky moons around gas giants, both of which must have formed after the Milky Way sufficiently increased in metallicity over time. This is actively being measured by NASA's Kepler Space Telescope as well as other Earth-based telescopes. We see, again, kind of rough ideas, 0.01 to 0.5. So the fraction of these particular stars that might have terrestrial suitable planets or moons is given by that second factor, F with a little p beside it. Now, the next factor is the N with the LZ. Okay, this is the number of planets that would be in the star's habitable zone, okay, or life zone. And we're going to be doing an activity for the lab activity this module that deals with Earth's or the habitable zones around planets. So habitable zone makes them Goldilocks planets, not too close, not too far from their stars, and so that makes them such that liquid water can exist. Now, although not very many water-bearing planets have been verifiably discovered, many candidates have recently been found. So again, we see a pessimistic value and an optimistic value. All right, and then moving on, so we've taken care of that one. Now F with the L beside it. This is the fraction of these potentially habitable water-bearing planets that life actually arises from chemical evolution. And there's really no way to even estimate this factor other than giving pessimistic values to more optimistic values. At least some constraints will be placed on the stars that may potentially harbor life on water-bearing planets. Of course, we have to take into account the fact that life on Earth took approximately 1 billion years to arise, which would eliminate short-lived massive stars. So stars that don't live long enough to allow their planets or their moons to evolve life would be kind of discounted. So that kind of limits the accuracy of that particular factor. Now we move on down to the f with the little l beside it. That's the fraction of life once it starts. Once we have simple life, what fraction will evolve and become intelligent enough to develop technology that we can communicate with it? And there's really no way to scientifically determine that factor. And finally, the last factor is even less answerable, and that's the fraction of the star's main sequence lifetime that an advanced technological civilization will survive, whether a short time due to destroying itself through nuclear war or climate change, or being able to survive a long time by avoiding such calamities. And again, there's no way to even begin to scientifically determine that factor. So we have to use kind of pessimistic and optimistic estimates.